Hello, my name is Elizabeth Hughes, and today I'll be sharing my findings from my case study action research project that focused on advancing fifth grade students' geometric thinking. This study specifically examined how intentional task design, guided by learning trajectories, the Van Hill model, and solo taxonomy can support deeper understanding of quadrilaterals. I'll walk you through my research process, including the problem of practice, methodology, instructional tasks, key findings, and implications for teaching and learning. Geometry instruction in many classrooms often emphasize identifying or naming shapes rather than reasoning about their properties and relationships. While students may be able to recognize shapes visually, they frequently struggle to explain why shapes belong in particular categories or how different quadrilaterals are related. Research suggests that geometric understanding develops gradually and requires intentional instructional support. This study was motivated by the need to design learning experiences that help move students along this trajectory beyond surface level recognition, but towards meaningful geometric reasoning. In my instructional context, I observed that many students remained at the early Van Hill levels of geometric thinking, specifically visualization and analysis. Their explanations often reflected multistructural thinking, where students listed properties but failed to connect them together. For example, a student might identify that a shape has four sides, four right angles, but could not explain how these properties relate to other quadrilaterals. This lack of connected reasoning limited students' ability to justify classifications or to generalize their understanding. To address this problem, my research question asks, how can learning trajectory align technology enhanced geometry tasks support students' progression in geometric thinking? This question, guided by the design of instructional tasks, the selection of tools such as GeoGebra, and the analysis of student thinking, the focus was not only on whether students improved, but how their reasoning evolved across the task. The Van Hill model emphasizes or describes how students' geometric thinking progresses through distinct levels. At the visualization level, students recognize shapes based on appearance. At the analysis level, they identify properties such as sides and angles. Abstraction involves connecting those properties and recognizing relationships among shapes. While deduction includes formal reasoning and proof. In this study, instruction was intentionally designed to support students' movement from analysis towards abstraction. The solo taxonomy complements the Van Hill model by focusing on the structure of student responses. At the unistructural level, students focus on a single idea. Multistructural responses include several ideas that are not yet connected. Relational thinking occurs when students integrate ideas into a coherent explanation. And extended abstraction thinking involves generalizing that understanding leads to new concepts. Solo was especially useful for analyzing students' written explanations and their justifications. Using both the Van Hill model and solo taxonomy provided a more comprehensive lens for understanding students' learning. The Van Hill model helped identify the type of geometric reasoning students were using, while solo revealed how deeply and coherently they were thinking. Together, these frameworks supported more precise instructional decisions and a richer analysis of students' progress. The study employed a qualitative case study action research design. The goal was to examine student learning closely while simultaneously improving instructional practice. The research was embedded within regular classroom instruction, allowing for that authentic observation of student thinking. Data was collected across a sequence of instructional tasks designed to progressively increase the cognitive demand. Students engaged in three tasks instructional sequence. Task one focused on identifying and describing quadrilaterals through a card sort, emphasizing initial classification and visual reasoning. Task two required students to classify quadrilaterals using GeoBoard, shifting attention towards properties and relationships. Task three asked students to design a quadrilateral-based playground requiring application, justification, and generalization of geometric concepts. Participants included a small group of fifth grade students in a suburban public school. Instruction occurred during their regular math block, ensuring that learning was situated within the normal classroom environment. This context supports the transferability of findings to similar instructional settings. Multiple data sources were collected to support triangulation. These included student work samples, GeoGebra artifacts, written explanations, and rubric-based observations. Collecting varied forms of data strengthened the credibility of the findings and provided insight into both student thinking and instructional impact. Student work was analyzed using indicators from the Van Hill model, levels of solo taxonomy, and learning trajectory aligned rubrics. Rather than focusing on isolated tasks, analysis examined patterns of growth across this instructional sequence. This approach highlighted shifts in reasoning over time. Findings indicated that students demonstrated increased use of precise geometric vocabulary and stronger relational reasoning as they progressed through the task. The playground design task, in particular, revealed evidence of extended abstract thinking as students generalized properties and justified classifications independently. These findings suggest that intentional task sequencing is critical for supporting geometric reasoning. Technology tools like GeoGebra can deepen understanding when used purposefully. Additionally, rubrics aligned to learning trajectories provide valuable formative assessment data that can guide instruction and support student growth. This study was limited by a small sample size and relatively short instructional time frame. Future research could explore similar task sequences across larger groups of students within professional learning communities or in coaching contexts to future examine instructional impact. In conclusion, geometric thinking develops progressively and requires instruction aligned to students' developmental levels. Combining the Van Hill model and the Solo taxonomy offers a powerful framework for both teaching and assessment. Thoughtfully designed tasks can meaningfully advance students' conceptual understanding of geometry. Thank you so much for listening to my action research project, and here are my references. Thank you. Have a great afternoon.